Good afternoon. Let me know whether the screen is visible. Is the screen visible?
Yes, sir.
Fine. So, welcome to the discussion on mission independent assembler features. As I said earlier, we have 5 features under this. We have seen 2 features of mission dependent assembler features, namely object code generation and program relocation. Coming to mission independent assembler features, we have 5. One of them is the literals, which I have seen in the previous class, where anything that is prefixed while defining a literal with an equal operator is going to be considered as a literal. As the name says, literal is going to, as literally, we are going to provide the data in the as a part of the instruction. When I say literally, probably there might be some confusion between literal and an immediate addressing mode. To avoid that, we have seen in the previous class, in the case of an immediate addressing mode, the value is provided directly like literal. That is a similarity between these two. But the major difference is while assembling the instruction, that means while object code is getting generated, in the case of immediate addressing mode, the value will be considered as a target address. That is, the target address is not the address per se, it is a value. Whereas in the case of a literal is going to be stored somewhere in the program, in the memory later, based on whether you are using a LTORG or not. And that location is going to be considered as an address. Thereby, an address will be involved while assembling the literal. That is the difference between these two. Otherwise, purpose is same. Next, LTORG is another assembler directive we have discussed, which means a literal origin, where if you use that, we can create a pool of literals. That means a pool of values or data that we are going to use in the program, so that we can keep instruction along with the data, so that the avoid for the format for instruction can be possible. Why we need to avoid format for? Because we have seen format for instructions are a direct addresses. They involve lot of modification records in the case of a program relocation. Thereby, to avoid that or to minimize that or to reduce that, it is advised always to have a lesser number of format for instructions. So by keeping both data and instruction together or close to each other within the range of a PC or a base relative, we can avoid taking the format for instructions. That is the advantage what we have with respect to the literals. That advantage was not there with the immediate addressing, because we don't have flexibility to keep the data separately. But using literal pools, that is LTORG, we have a flexibility of grouping the data and putting wherever is possible. So that is what we have discussed as a literal. Now let us look at the other concepts of mission independent features. The second one is a expression. Probably today we touch upon expressions and symbol defining statements, whereas program blocks control sections require at least a 1 hour each to identify what they are. So let me try to cover the next two, the expression and symbol defining statements. Now, let us look at the symbol defining statements. As the name says, symbol defining statements, we have symbols, meaning labels. We have used labels of our own choice. We have created our labels. We have used LOOP, LOOP1, copy, depending upon the type of program you have. So that is our discretion. We can create the labels. So we have done that. Now, in addition to that, we also have a flexibility to have a label at later point of the program and give some value for that. Actually, there are 2 purposes of this. We'll see that very soon. And those purposes are like your, probably I can say your preprocessors. We have a hash define in C++. What is use of hash define? There, for example, you might have done hash define pi 3.17. You write the program, you are going to use area of a circle is equal to, let us say, pi r square. There, instead of writing 3.17, you will be writing pi, which you already defined as a define statement, then radius into radius. So what was the advantage of that? There are 2 advantages in high level language. One, it is very easy to read, so improves the readability. Second, whenever you want to change the value, suppose suddenly you want to change 3.17 to 3.1742. So if you have a defined statement, you can directly go to the beginning of the program. At one place, you can change 3.17 to 3.1742. It will be reflected in the entire program. Suppose if defined statement is not there, you have to search the program where the value 3.17 is there. At all places, you have to do 3.1742. By chance, if you miss one place during the search, you may lose the context. So it is going to have dual advantage. One, improves the readability and improves the modification of the value, with which we can avoid the debugging problem. That is, errors will be less. So two purposes we have seen high-level languages with respect to hash defined statements. Similarly here, your symbol defined statements are available. So first, if at all you want to set a value, for example, you are having a loop. That loop is nothing but having 100 values. So if that is the case, instead of having loop always for various numbers, I will create a counter where the counter I will set as 100. So if that is a requirement, how do I do that? That is possible using our symbol defining statements. So the first purpose of symbol defining statements is to improve the readability again. Second, to provide values in the object program while dealing with the some of the registers. We'll see both of them quickly. But before that, the concept of a symbol defining statement is that the user defined labels, whatever we are going to have, they are serving a purpose to some extent as far as the labels are concerned. No problem. We have been using them so far as a loop variables. Now, if you want to use them as a variables, still we can do that. But for that purpose, we require another assembler directive, which is named as a EQU. So there are two symbol defining statements we'll see now. One is a EQU, other one is ORG. The first one let us take. So now the concept is symbol defining statements are similar to your hash defined statements in high level language, which will provide two purposes. One, readability, and if at all you want to do any modification or debugging, that is possible. Same concepts are here. At the same time, we can have these symbols to have some values also. So far symbols were not having values. Now if you want, you can do, but you need to use a EQU, which is another assembler directive. Since it is assembler directive, let us go back to the 2-page which are reserved already. I think yesterday we have taken LTORG. Now we can add one more to that, that is EQU. You have a list of assembler directives. So add EQU to that. So EQU, the purpose is to define symbols with values. That is the purpose. You can make a note of that and you can update the table, what you have reserved already for these assembler directives. Now, with that, let us come back to this. So now we have a symbol and we want to attach a value to that. That can be done using EQU assembler directive. The format is like this. You take the label name, for example, counter, count, whatever it is, some number. So that number you want to provide to that, number you want to provide to the symbol. What you can do, counter EQU 100, count EQU 50. So like that you can assign. It is similar to your I is equal to 10 type of concept. Or max is equal to 100, you might have used it for a boundary for an array. So those type of statements you want, you can define like this. So symbol followed by EQU and followed by the value. So example is written here. Since we are defining labels, and so far how the labels were treated in pass 1, the labels were stored in the symbol table along with the addresses. Similarly now, since these are also labels you are going to create, they need to be stored in the symbol table. So all those values or variables that you are going to declare using symbol, EQU, they also will be stored in the symbol table. That is your SymTab. So this is how we are going to have a EQU to define various symbols with values. The advantages we have told, they have two advantages. A specific advantages of EQU. One, as we said now, to increase the readability. For example, you have defined now counter with 50. Tomorrow you want to change counter to 60. You can simply go to that one place and make counter as a 60. It is going to enhance the readability. That's what we know. Similarly, the next advantage is to have a mnemonics for all the registers. So before we get into this, let us make sure that you understood the first concept, that is how to define the EQU. So may I have some responses? If you have understood how the first part of EQU is used to define the values for the symbols. Any response? Understood? May I have some response?
Yes,
understood?
sir.
Fine. Now, let us look at the next advantage. The next advantage is to look at registers. So if you recall, we have 9 registers in SICXE. We have 5 registers in SIC. That is accumulator, index register, link register, program counter, status word, base register, floating point register, and 2 general purpose registers. And that is not a big deal. The importance is A has a number 0, X has a number 1, L has a number 2, B has a number 3, F has a number 6, SNT has a number 4 and 5, and PC has a number 8, and SW has a number 9. But how do you remember them? It is not possible. Second, when you write a program with involving these registers, you know how to convert them. So you have to go to the actual numbers and convert their equivalents to machine number, which is a mnemonic. For example, we have used in one of our division program RMO A, S. When we say RMO A, S, this is a typical format 2 program because A and S both are the registers. So format 2 is nothing but a 2-byte opcode R1, R2. When you write R1, R2, what is A, S? They are not the addresses. If you search in the entire program, you will not find any value for that because A and S are nothing but registers. So what is the value of A? 0. What is the value of S? 4. So you remember those values and write. Since we are humans, we can refer to the manual and I can write the value, or I can by heart if it is a simple architecture. But how about the system? Now we are working on generating a system software, meaning a software package that will deal with all this. So imagine now, whenever we return RMO A, S, how does the system know what is A, what is S? So it is our responsibility again to inform the system that A is equal to 0, X is equal to 1, L is equal to 2, PC is equal to 8, SW is equal to 9, B is equal to 3, and so on. If that is the case, we have to create a information in the program such that your system will use them. So for that purpose, you can use the EQU because we know the value of A is 0. We know the value of S is 4. So before I write RMO A, S, I can simply define A is equal to 0, S is equal to 4. Internally, that value will be used at the time of a object program creation. So this is the second advantage. That means whenever you want to use registers in the program, then those typical mnemonic values also need to be provided. So the best way to provide them is using EQU. So 2 purposes of EQU are: 1, to improve the readability. For example, symbol EQU some number. For example, count EQU 10. Second advantage is to define various registers with their internal mnemonic values like A, B, S, T, F, S, all those things you have used. For them, we have a typical values and we need to use those values only. If that is the case, we can use our EQU statement for the purpose of defining. This is one set of symbol defining. So symbol defining statements, there are 2. One is EQU, other one is ORG. Under EQU, there are two again. One is for the readability point of view, and using that, we are going to assign the internal mnemonic values for various registers as and when we use them in the program. So with this, EQU purpose is done. Let us look at the second one, that is ORG. So ORG is nothing but origin. Like LTORG, we have another one called ORG. Again, you can add that as an assembler directive in the list. In the 2-column list, you can add that. So add this ORG as another assembler directive, which means that origin. That means we are going to provide a separate address for the instruction wherever ORG is involved. So ORG main significance is to assign addresses explicitly. That is a concept. ORG mainly to assign the addresses explicitly. Remember this. This might be an example for an innovative question for you. Tomorrow, we may ask you, discuss the assembler directive using which the addresses can be assigned explicitly. Normally, it is done through LOC-CTR. You just give a starting address, keep on adding 2, 3, 4, depending upon the size of the instruction. You cannot do anything. But using ORG, you have a flexibility where you can provide the or assign the address explicitly, meaning that you have a liberty to have the address of your category, address of your requirement. So if that is the case, explicit address assignment is done using ORG assembler directive. That we can make a note of it. So ORG, as the name says, it is going to origin of your data, which is used to represent or provide or assign the addresses of certain values or certain locations. We'll see soon how it is being done. And that value is completely based on the LOC-CTR. So LOC-CTR, we know that is one of the variable using which we can keep on tracking the addresses of individual instruction, which we have done in the past one. Later that we have not used location CTR anymore. That is LOC-CTR. So the main purpose is to assign the address, which was an activity in the past one. So that is done. Once that is done, now we are going to use location LOC-CTR again with ORG, where the assembler is going to reset the value of location counter to the desired value of our choice. Let me take a context where this ORG can be visualized. Assume I have an array declaration. I have a location of my array starting from 2000. I've declared 100 values. Let us say 100 bytes, 100 characters. So 2000, 2001, 2002, up to 2099, I will go. This is my value. Suppose I use RESB and I reserve 100 bytes. What is going to happen? It's only memory reservation. But if at all I want to load the value at 2001, 2002, 2003, 2004, I should go to a loop, go to the loop and have this value being stored. Or I should have a provision such that from 2000 to 2099, I will initialize the data, then I will go to the next instruction. If I do not take care of this, my system will simply reserve 100 bytes and it will jump into the next instruction. So what is the requirement here now? When there is a need to allocate the memory and at the same time assign the values, then we need to go for a ORG. Otherwise, what will happen? It will only assign the memory, but in data will not be initialized simply because your instruction will just continue with the next instruction when you are especially dealing with a RESB or RESW. So that is the kind of issue we might be having. So as a solution, we have a ORG. So coming to the discussion, the need for ORG is with regard to assigning the memory and initializing the values. If that is the need, then we need to have a ORG in place. So what is the structure of that? So we have seen the structure of EQ. Left hand side there is a symbol, right hand side there is a value. That is the need of a EQ, because there should be some label attached with a value. But coming to ORG, it is not dealing with the labels, it is assigning some value to location counter. So by default, the LSH is nothing but a location counter. So you need not specify that, you can directly say ORG value. So typically the formats are same here. For the EQ, left hand side there was a symbol, right hand side there was a value. For ORG, left hand side is not given because by default it is a LOC CTR, thereby we need not give that. So right hand side value remains same. Now let us take an example of this now. As we said, I am at location, let us say 2000. My instruction at 2000 is STAB RESB 1100. So STAB is a label, RESB is my assembler directive, which is going to help me to reserve 1100 bytes. So these 1100 bytes I will be reserving now onwards. So when I go to next symbol, that is SYMBOL RESB, so my address will be typically 2000 is my STAB address plus 1100. Assume this 1100 is hexadecimal, because normally address to be in hexadecimal. Don't waste your time in converting decimal to hexadecimal. Assume 1100 means is hexadecimal. Now my 2000 plus 1100 will be 3100 is the address for SYMBOL RESB 6. Similarly, my address for value RESW1 will be 3100 plus 6 and so on. We know how to do that. Now the problem here is I have declared a memory 1100 bytes at 2000 location, that is STAB. But I want to stop there, provide some values from 2000, 2001, 2002, 2003 up to 3100, then come back to symbol. In the absence of ORG, I am unable to do that, because the once I declare STAB RESB 1100, it allocates memory and goes to that memory, that becomes the address of the next instruction. So I will not have any provision here to deal with that type of data unless I use a loop. With loop, yes, we can do. We have done that earlier as well. But now, is there any other mechanism without that? Because I need not go to loop always. So there is one mechanism. Now I will put ORG. So when I put ORG, what it is going to do now? It will say, now what is the meaning of ORG now? My location counter is 2000. My location counter has gone to 3100. Again, I am bringing back to 2000 because ORG STAB. What is STAB? 2000. What is ORG? Assembler directive, which will reset location counter based on the value. What is the value? 2000. Now, your location counter is changed to 2000. Now, at 2000, you have some data. You do whatever you want between this ORG and another ORG. All the data you can start using and putting into the location. Once your purpose is over, you have to bring it back to the normal value. What is the normal value? 2000 plus 1100. That is the actual value you are supposed to be. But for your requirement, you have meddled with this and you have used the data in between. So once purpose is over, you have to reset the location counter with old value. The old value will be STAB plus 1100. So that is the need of a ORG. So two things what you have to observe here is ORG is a special assembler directive using which we can assign addresses for various labels or various locations explicitly. Second, by using ORG, you have a flexibility of assigning the data or providing the data at the same time, assigning the address at the same time providing the data. So address and data both can be handled together with ORG. So that is the idea behind ORG, which is a symbol defining statement. So quickly let me know if you have any doubts. Maybe 2 minutes you can take. You just observe both EQ and ORG. So meanwhile, I will take the attendance. May I have attendance? Asta?
Present, sir.
Abhinav?
Present, sir.
Aishwarya?
Present, sir.
Ambarish? Anu?
Present, sir.
Arbaz?
Yes, sir.
Arjun?
Present, sir.
Ashok?
Present, sir.
Vinita?
Yes, sir.
Present, sir.
Bhargavi?
Present, sir.
Ambarish, idiyanappa?
Yes, sir. Idini,
Avisha?
Present, sir.
Chaitra?
Present, sir.
Chatterjee? Diksha?
Present, sir.
Present, sir.
Chatterjee? Deepika LG?
Present, sir.
Deepika MB?
Present, sir.
Murli Krishna?
Present, sir.
Gangubai?
Present, sir.
Guriya Kumari? Harshit?
Present, sir.
Sunjar? Kavya?
Present, sir.
Kishore?
Present, sir.
Kishore?
Present, sir.
What happened, Kishore? Again you were absent for 3 days?
No, sir. 2 days only, sir.
Yeah, yesterday, day before, 25th, 29th and 30. Lata?
Yes, sir.
Manisha?
Present, sir.
Manjunath?
Yes, sir.
Nayana?
Present, sir.
Nishant?
Present, sir.
Nilanjan? Nilanjan? Pavitra?
Present, sir.
Maithili?
Present, sir.
Priyanka?
Present, sir.
Pavan Kumar?
Present, sir.
Akash?
Present, sir.
Rajeshwari?
Present, sir.
Rakesh? Ramya? Rashmi?
Present,
sir.
Ravi Shankar? Rizwan?
Yes, sir.
Present,
Vishal?
sir. Present, sir.
Savita? Shruti? Sneha?
Yes, sir.
Spurti?
Present, sir.
Srinidhi?
Present, sir.
Srinivas? Sunil?
Present, sir.
Vaishnavi?
Present, sir.
Vinny? Okay. So any doubts in symbol defining statements, EQ and ORG? Hope you have added them to the list of assembly directives. Now can anyone tell me how many assembly directives you have? How many have covered so far?
Eleven.
11. Okay. Fine. The next concept is expressions. The third idea or third as mission independent assembler directive is expression. We have seen literals, we have seen symbol defining statements. Now we have expressions. So expressions are those which we normally use typically in our high-level languages as well, which is a mathematical expressions or arithmetic expressions. So expressions also can be used as part of the operands. So far we have used LDA, say location, STA, some value. So like that, we have used only single operands and single labels. Now it is also possible to have expressions also part of our operands. So some of the examples we can see here. I've defined length, EQ just now we have used location 1 minus location 2. That means I have two location values. The difference between that is a number that becomes a value for length. Similarly, I have used NUM EQ location 1 minus 20. 20 is a number. Location 1 is also number. The difference between these two is going to be some number at the end, and hence it is also possible to be an expression. One more important special symbol is star. So star is also a type of expression which is going to represent the value of the location counter. When you say LOC EQR star, star means the location counter. At present, whatever the value we have in the location counter, that value will be assigned as a value. That is the meaning of a star if it is used in the operand value. If it is used elsewhere, it will be comment. If used in the operand value, star represents the current value of the location counter. So this is how the expressions can be created or used. But at the end, each expression should give a single value. There should not be any ambiguity on that. So that is a kind of expressions what we are looking at. Okay. Similar to your mathematical expressions you might have used or any high-level languages we have used. Now, how these expressions are made of? These expressions are made of using two types of terms. One is an absolute term, other one is a relative term. What do you mean by an absolute term? An absolute term is one which is going to have the value directly. For example, I have a location 1 minus location 2. So wherever I am in the program, whether my program is at 2000 or 5000 or 10,000, the location 1 will have some value, location 2 will have some value. The difference between that is always a constant, is the same value. For example, my program location 2000, I start. Location 1 is at 2010. Location 2 is at 2020. What is the difference between these two? Location 1 minus location 2, 2010, 2020, 10 is the difference. Suppose my program is relocated somewhere, it became 7,500. So from 2000, my program starts at 7,500. So what was there at 2010 will be at 7,510. What was there at 2020 will be at 7,520. Now what is the difference? 7,510 minus 7,520 remains same. So it doesn't matter. That means the terms which do not bother about where the program is. In other words, if the program relocation is not going to be troubling you, or the terms which are independent of program relocation are going to be called as a absolute terms, meaning that it doesn't matter how they have been defined. It doesn't matter where is their position. Their value is always same. If that is the case, we call them as a absolute terms. But there are certain terms which will depend on the relativity of the program. For example, take the second, NUM EQ location 1 minus 20. So location 1 today is 2010. Tomorrow it will be 5025. Day after tomorrow it will be something else. If that is the case, I don't know what value I am going to get. Value might be differing. So 2000 minus 20 becomes 1980. 5000 minus 20 becomes 4980. Definitely there is a change in the value. Why it is changing? Because this particular term is relative to the starting of the program. If the starting address changes, the value also changes. Whereas in the previous example, it doesn't matter. The value remains same. The typical difference value is going to remain same. If that is the case, an absolute value or absolute term is one which never depend on the program relocation. Whereas the relative terms, as the name says relative, they depend on the beginning of the program. So what is the third example? LOC EQ star. What type of term it is? Is it absolute term or relative term? What type of term it is? LOC EQ star. Is it absolute term or relative term? Any answers?
Relative.
Relative. Why? Because it depends on the location counter. Location counter value will keep changing, which is relative to the starting of the program. So good. So the star is a relative term. So like that, we have these two expressions. Now the expression, if you want to define, expressions can be two types of expression based on the absolute and relative. If I am using only absolute terms, my expression is going to be called as a absolute expression. If I use only relative terms, I call that as a relative expression. That's all. So expressions can be two types based on the type of terms what we have. They can be absolute expression if they involve only absolute terms, or they can be relative expressions if they involve only relative expressions, so relative terms. That is what the concept of a expression. So what you have to understand here is expressions can be used as an operands which are going to ultimately result in a single value, and they may be based on a direct labels or symbols, or involved with some other constants, or maybe the difference between two other labels. It can be of any kind, which is pretty same as in arithmetic expression, and those things are going to be part of our operands. If that is the case, we can also use them as part of our instruction. That is the kind of discussion what we had as far as the expressions are concerned. Now let me know what type of terms each one of these. I have 5 here. Can you tell me what are these? Are they absolute terms or a relative terms? What type of terms are there? What is the first one? RET, ADR, RESW1. What type of term it is? Is it a term? RET, ADR, RESW1. What type of term? It is absolute term, relative. Who to remember how to tell? If it is depending on the starting address, it is an absolute, so it is a relative term. If it is not depending on the starting address, or it is independent of relocation, in other words, it is a relative term. What is the first one? RET, ADR, RESW1 is absolute term or relative term? Give some answers. You have some answers.
Sir, absolute.
Which one? First one. Which one is absolute?
First one.
How? What is it?
Sir, there is no address of location.
No, for every instruction address will come, no. This is an instruction. RETADR is a label. RESW is assembly directive 1. So RETADR is a label. So label address will change with respect to starting address or not?
Yes, sir.
Then what type of term it is? It cannot be absolute. It is a relative. It is relative to the starting of the program. Even the second one, length, RESW1, it is relative to the starting address of the program. Similarly, the third one, buffer, RESB 4096. The address is again relative to the starting of the program. Even buffend, we have just now seen. So all first four are a relative terms because depending upon the whatever the starting address we have, that value will be changing. But look at the fifth one. Irrespective of the address what we have for buffend and buffer, the difference will remain same. So max length will be always same number, irrespective of whether we have a program relocation or program relocation is not there. The max length is same. Then max length is an example of a relative term. So that's what we have as far as the expressions are concerned. So this is for the today's class. So I'll wind up the class here now. If you have any doubts for the test, so probably we can discuss.